Okay, so this practice is not meant to be the only study guide for the exam, but this is more to give you an idea how the questions would be. If you scan through the problems, you can see I won't be asking like multiple choice questions. It's mostly going to be like numerical questions where you have to solve for something, as we did in the homeworks and in the class examples. All right, so I'll solve. If there's any question, just as I mentioned, let me know. And I can go back and discuss that. This is a Word file, it's not PowerPoint, so I don't know how good I will be here, but I didn't put them in PowerPoint format. What color should I pick? Let's try this one. So find the reaction forces at A and B. So that's coming from the equilibrium chapter. So we have this one and this support. This one, as you can see, it's a pin, whereas this one, that's the smooth surface. So this would provide me with two reaction forces. One, let's try if I can, RA in the Y direction and RA in the X direction. We have 4 kilonewton at a distance of 6 meters away from A and 2 meters from B. B is inclined with this surface. So we will have a normal force that's going in this direction. So this one is RB. All right. So that's actually 90-degree right here. Now I need to find those. First, double check before you continue. How many unknowns do we have? We have RAX, that's one, RAY, two, and RB, that's three. Three unknowns. Can I put RAX equal to 0? No. Although the force is parallel, it's perpendicular to the cantilever. However, you can't put it because RB is not parallel, and RB is going to give you two components. One would be in the negative, based on what I have here, I'm going to have RBX and RBY. Okay. So as you can see, I'm going to have RBX due to RB being in that inclined direction, and it's not equal to 0. Why? Because I have RB that's a result mainly due to RBY, but because it's inclined, it's also going to give me an RBX, and we're going to see it. But now the question is, well, it seems I have 1, 2, 3, 4. No, those two red RBX and RBY, those two are function of RB. Okay, so it's going to give me RB cosine and RB sine, but which one is cosine, which one is sine? I can't tell until, probably I can because I solve a lot of these problems, but if you can't see it, just try to draw. Yeah, it's too small here to put everything. That's 30 degrees. I have a 90 degree here. That's RB. And then I have the vertical. And that's also 90 degree. So this would be 30 degrees, right? Because this angle, that's the 30, and let's color this. Let's call this alpha. So alpha plus 30 equal 90, and then this is 90 degree because that's RB, it's coming here. Therefore, this angle is, excuse me, this angle is 30. Why I need that? Because now I can decompose RB, or yeah, RB into two. This one, the vertical, would be do you see the angle? That's RB cosine because it's adjacent to the angle, whereas the X component, that's RB sine because it's away from the angle. So now I don't have RBX, actually. I have RB. I can leave it, but just in order not to be confused by how many unknowns do we have. This would be sine 30, and this would be cosine 30. So now we're down to three unknowns. Maybe I can't solve it as we did before in 1, 2, 3. Actually, we should. Uh, but we have three unknowns. I should be able to solve this. How many equations do we have? We have summation of fx, summation of fy, summation of moments. Since I have three unknowns, rax, ray, and rb, then I'm going to need to use all three equations because those are three unknowns. Usually it's faster if we start with, because I can see 1, 2 in the x direction, 1, 2 in the y direction. So probably if I start with the moment equation and I take it about the point that has the most number of unknowns, which one is that? That's point, although it's going, I should help me if I take it B, it's the same. But if I take it about point A, that means ray and rax are both going to disappear from my equation because they're both passing through point A. So rax times 0 plus ray or minus ray times 0. That's just going to disappear. What do we have? I have then left 4 kilonewtons. It's going in the clockwise. So minus 4 times 6, the perpendicular distance from that force to point A. And then I have RB cosine going in the counterclockwise. So plus RB cosine 30 times 6 plus 2. Okay. And then this horizontal is passing through point A. So it's not going to create any force. So that's any moment. So that's equal to 0. Therefore, RB is, I'll take this. So it's 24 to the right side. And then divide by 8 cosine 30. So as you can see, I can get an answer here. 24 over 8, that's 3 over cosine 30. I'll get a positive value. That's number 1. So, and it should be positive because, well, no, I can't tell. I can't tell just from that diagram if it's pushing up or down. But anyway, we got a positive value. So we're done with RB. I'm not asking you to do cosine and sine, but we need those when you do the balance in the X and Y direction. Okay. So next, it's up to you which one you, since I solved now this, I solved this. So I can solve either the X or Y, and I should solve for the two other unknowns, rax and ray. If I do the F in the X direction, I have rax going in the positive, and then minus RB sine 30 equal to 0. That's it. The 4 kilonewton is in the Y direction, so we don't have that. Therefore, rax is RB sine 30, so that's 3.46. So that's equal to 1.732 kilonewtons. The same way we'll do the Y. I have ray minus 4 and RB cosine 30 up. So minus 4 plus RB cos 30 equals to 0. So therefore, ray is 4 minus RB cos 30. And that's equal almost to 1 kilonewtons. And that's it. That's all they asked us to find. Find the reaction forces at A and B. All right, question 2, we have, this is again, it's a truss system, so I won't be pushing a lot on these in the exam. Probably that that would be the max that you would see for these systems, because it is part of chapter 4 where you have to, when we did, if you recall, 428 in the homework. I'll ask if you have any questions after we're done uh, related to the homework. But 428, which I solved in the class, we saw how we can uh, take the free body diagram for multiple systems, multiple points. So each pulley by itself in order for you to be able to solve it. And that's actually the question. They're asking you to find the force in each member. And that's why those are usually called trusses. It's not a real truss, but it is kind of, because we need to look into the internal force inside these. Before you do that, I have to check which point I can start, or maybe points, not just one, which points I can consider to solve for this system. If you look at A, you have two reaction forces because this is a pen, this is a roller. So you have RA and RA. So that's 1, 2, 3, 4 unknowns at point A. If I take point A, I have 4. So I shouldn't start with that. How many equations do we have for such systems when we take points? Those are called coplanar concurrent, which means the forces are passing through the point, so you can't use the moment equation. So the max that you can have, the maximum number of unknowns that you can have at each point that you consider shouldn't cross 2. Again, C has a reaction force, so that's one unknown here. And I have this, 2, 3. So also I can start with C. And usually we try to avoid to solve for their action forces and then start solving if there are any other ways to solve for what you're asked to solve for. That actually leaves us with only one option, which is point B, but we'll do more of these in the truss, the next chapter. Why? Because point B is right here. I have this one, which is connected to the 70 kilograms. So whatever that force is, 70 times 9.81, that would give me almost 686.7 newtons. So that means that's the weight, that's the tension down here. So that's known. And then I have one, two, so two unknowns. So I'm going to start with joint B. Again, that's the only option that we have here. But in some other problems, maybe you have some other points that you can consider. I have 686.7 newtons. That's the tension in this wire or cable. And then you notice here 2, 2, 2. So that's that would split this angle equally between the two. And because I'm gonna need to decompose or find the component of these two forces. However, they're not going to be, let's see, FAB. Actually, we should get the same answer. Let's check. I'm just trying to check my word. So FAB is up. What's the slope? Since this is isosceles, so therefore it should cross this in the midpoint. Therefore, it's 1. One here. However, I don't have the x. Usually we have 1, 2. So I would say 1, 2, and here's square root of 5. No. Here, actually, we have this side and the hypotenuse, since the 90 degrees here. So that's 1. I don't know how small it is, but let's zoom in into that. So this would be 1. The hypotenuse is 2. Therefore, it's too thick here. So the hypotenuse is 2. Okay, so what's the side, the horizontal portion? It's 2 square equals 1 square plus whatever you want to call it, x square. Therefore, x is 2 square, 4 minus 1 equals to 3. So x is square root of 3. Okay, I do need to lay down the slope first before I start to find the components. I mean, I need both. Okay, what about the other one? It should be the same. I have one here on the y and the same, the hypotenuse is two. Therefore, this one, what is it? I don't want to scroll down. FBC. And then we have one and the same here. That's two. And this one is square root of three. Okay. Let's now decompose those. Let's now zoom out. So I have FAB. That's this force. The x component is square root of 3 divided by 2. And FAB, that's the y component, 1 over 2. Okay, the y divided by that. The same way we can do FBC. I'll have FBC, I'll put it here. FBC, the x component is square root of 3 over 2. And FBC, 1 divided by 2. Okay, so as you can see, all forces are now passing through that point. So I can now, that's why we said you can't use the moment equation. So I'll do summation of forces in either way because I have one, two unknowns. In the y, I have one, oh, actually, and two. So in both cases, I have two unknowns. So it doesn't matter which one you start with. You're going to have to solve two systems, two unknowns. The x component would be minus square root of 3 over 2 times FAB, this one, and then minus square root of 3 over 2 FBC. Okay, I have nothing else. So that's equal to 0. Then we'll do the y. So I have FAB 1 over 2, this one, FAB minus half FBC minus, don't forget this force, 686.7 equals 0. Again, we solved many of these in the previous chapters. You can use the elimination method or the substitution method. I'm going to use the calculator here. This is just a review, but if you can't find it, just let me know. Let's see, where's my calculator? Okay, so number of unknowns is 2 minus Actually, it's not that hard. It's not that complicated. Here we're gonna get, if you notice, it's the same coefficient, this and this. So we're gonna get FAB equals minus FBC, right? This is actually much easier than solving this whole thing. And here also they're the same half and half. So I'm gonna get FAB and minus FBC. That's another FAB, and then minus 2 into 686.7 equals 0. So 2FAB equals 2 into 686.7. So FAB is 686.7 kilonewtons, and FBC is minus 686.7 kilonewtons. Okay, now let's check. We have this one as well. Do we need to solve for that? What do they ask? Find the force in each member of the simple structure and state if it's under tension or compression. That's, we're gonna ignore that. We'll do that in trusses uh, to check if it's tension or compression. But either way, since it's like pulling out, it's tension if it's positive. So I need now this one, AC, FAC. If I consider this joint A, then I do need to find the reaction force here. Or if I consider point C, I do need to find the reaction force. Since this has two, I'm gonna not solve for that one. I'll try to find RC. How do we find RC? We'll go back to question one. How did we find the reaction forces? We'll take the moments, summation of force, or summation of force for X, Y for the whole system. In this case, sorry, I can't, I have to keep scrolling up and down. But if I take the moment for the whole system, so if you take the whole system, you're not taking sections here or here or here. I'll need to solve for A right here. So I'll write it for you, whole system. We'll take sum of the moments about point A equals 0, because I need to get rid of the reaction forces at A in order for me to be able to take, to consider joint C. Actually, just, oh, okay, sorry. I don't need to do that because if you look at C now, we already solved for FBC. I have FBC, I have FAB and RC, so I can just simply consider this joint at point C, but I'm going to solve it in both ways for you. I'll solve for RC first, considering the whole system, and then we'll look into just as a check to do this, this, and this. One time from point C, one time from the whole system. If I take the moment about point A, I have RC is rotating in the counterclockwise. So RC times 2 meters. And then we have the 70 or the 686.7. It's rotating in this direction. So it's minus 686.7 into, what's that one? We said that's square root of 3. We just solved it. It's the same as the slope. So the distance from here, from this point to point A, that's square root of 3. I didn't realize it's going to be that complicated to solve for RC from the whole system. So this times that, that's it. That's all the forces that I have. equals to 0. Therefore, RC is 686.7. Take it to the right side and then divide both by 2. That would give me 594.7 newtons. I don't need RC, I just need this one, AC. So as we did up there, I'm gonna take joint C. I have RC. We did say it's going to the right and we get a positive value, so make sure it's going to the right. The other force is FAC. That's the one we're trying to find. And then I have FBC. And it has the slope, which is 1 and 2. 1 square root of 3 and 2. I'm gonna decompose FBC. It turns out we don't need RC at the end. So we just did this for nothing. So why? Because if you put here FBC square root of 3 divided by 2 and FBC the y component, so 1 divided by 2, we already solved for FBC. We already got that. It's right here. Okay. If you look into the y, I have 1, 2, that's it. So I didn't need RC. Because if you take now summation of force in the y direction equals to 0, I have FAC going up plus half FBC, that's it, equals to 0. So FAC is minus 1/2 FBC. FBC was minus 686.7. So divide that by 7, we will get the answer as positive. So it would be 343.35 Newton. Okay, questions? Again, I could have started from this joint, which I should, just to check if I need to solve some extra steps, because it turns I don't need this, because we already solved for FBC. I already solved here for FBC. So I only need the y direction of this force at this joint, the force balance, and then we can find FAC. Just wait 1 minute, just in case you're still writing, and then we'll move to the next question. Okay, the next one we need to calculate the couple moment. I have this structure, it's a beam that has two forces, 10 kilonewton here and 10 kilonewton on the left. They're both parallel because this one is 4 to 3, this one is also 4 to 3. But if you try to find a couple created by those two, you need to either find the line of action and then try to find the perpendicular distance. Remember, the couple is force times perpendicular distance, or you will you can, and this is very close to what we did in class, sorry, not in class, in the homework. So if you decompose, if you check the moment, the components of this force here, you will get one force to the left, that's 10 times 3, the x component, over 5, the hypotenuse. And the y would be 10 times 4 divided by 5. If I look now to the left side, I have 10. I have 10 here times 3 divided by 5. And here 10, the y component is 4 divided by 5. Okay. Think about it. Try to find the couple. I just need to grab something and I'll be back in 5 minutes or so. Mhm. All right, I'm back. We get any answers? Final. What's the total? Do you want me to call names? Or do I have any volunteers? Aubrey, did you get any answer?
I'm still working on it.
Okay. So remember, couple is force times distance. So you have to be looking into a common force that meets the criteria for what we call a couple. So it has to be the same force, but in opposite direction. For example, the 10 4 over 5, 10 4 over 5 in the 2y direction going up and down. So that's a couple. And then look for the distance. It's 4, right? However, this problem is slightly different. I'll give you maybe 2 more minutes to see if you can figure it out. Can we stop, pause the, actually, okay, so as we've said, couple, it has three portions. First, it has to be the same value. For example, if we look into those two portions, the 10 4 over 5 or 40 divided by 5, that's basically 8 and 8. Uh, what is it, kilonewton? This one is 6 and 6 kilonewton. Okay, so the 8 and 8, that meets the first criteria. It's the same value. The direction, the one on the right is going down, the one on the left going up. So that's the second one. So that's a couple. Third, the one of the characteristic to calculate the couple, I need to find the perpendicular distance. So those two, the 8 and 8, they're like that. So that's the vertical force. It has to be the perpendicular distance. So that's this distance. And that's why we did the components in the first place. That's how we solved the one in the, I believe, either the homework or in the class. But the forces were actually acting exactly on this line. So the two X forces, they were just passing through each other and canceling each other. So they didn't create any couple. Whereas here, as you can see, they're away, so they would cancel. They would cancel just the force, but they would also create a moment that would rotate this way. Since it's 6 to the right, 6 to the left, this one, 6 to the right, this one, and they do have a perpendicular distance, which is from here all the way to here. So it would create a couple that has a distance of 2. So this one is 8 kilonewton, 8 kilonewton. That's the first couple. It has a distance of 4, and it's going in this direction, so clockwise or negative. The other one is this direction, this direction. It's 6 kilonewtons, 6 kilonewtons here, and the distance is 2 meters, and it's going in the counterclockwise direction. Okay, so the first couple, this one, it's minus because it's clockwise, F times D, so minus 32 kilonewton meter. The second one is going counterclockwise, so M2 is 6, it's plus, times 2 meters, so it's 12 kilonewton meter. So now what's happening? They're asking us to find just it's tricky. If they say resultant, then you would know we have to, but they just want the couple just to make sure that you know you can find both. This is actually, I believe this was an exam question. So now at any point, I might ask you, find the moment here. So you have to do it on your own. So you have to know that I have two moments or two couples, and they're going in opposite directions, and we can see it in the sign. So the total M at any point is minus 20 kilonewton meter, or you could say 20 kilonewton meter in the clockwise direction. This or this one. Okay. Let's move to question number 4. We'll give 1 minute again, just for you to finish. So all right. So we have this beam, and we have 2 supports. Both are pin supports. We have 3 forces, 800 Newton. Oh, it's not zooming in. Okay, we have the 800 and 600. They're acting at this point, at the same point. And we have this 600 acting at this point down. You might ask a question if you just look there without reading. You might start actually solving directly for the support forces. So the question would be, hey, you said you're not going to give us 2 pin supports. I can't solve this. Which is partially yes. Because you don't have to put these because. So we have 4 unknowns. I have 3 equations, summation of force in the x and the y and the moment. Well, how can we solve that? Well, just if you read part A, part B, and that's why I put that big note down there, they're asking you to find the resultant of the moment and the forces. So this is not an equilibrium problem. This is the very last section of chapter 4. We need to find the resultant of these forces and moments that would be created by looking at one time at point A and one time at point B, and then I don't know what's point C, but we can read it. But they're not actually asking you to find the reaction, so you're not balancing the problem. They just want to find the resultant. I said the difference between finding a resultant and trying to balance the system. Balancing, then yes, I need to give you 1 pin, the other has to be roller in order for us to be able to find the support or the reaction forces. In this one, I just need to find the resultant of these forces, okay? So let's start with A. First resultant, that means I need to find RAX and RA. Again, this is the resultant, not the reaction forces, so whatever you want to call it. So I can say, just to remove any confusion, Rx at A. So it's not Rax, the reaction force, and Ry at A, and then the moment. We'll do it in just a minute. But let's take a look. What do we have? Rax, there are no forces actually in the X, so that's equal to 0. I'm not going to have any resultant at A. I will have a resultant at in the Y direction. What's that equal to? I have minus 800 plus 600 minus 600. So minus 800 plus 600 going up and minus 600 going down. And yes, I can remove those 2 and put 200. Okay? But it's actually split this way for a reason. Maybe to cut some time on you, I don't know. But if you notice, we have 600, 600, and that's when we need to do the moment. So that's like an extra practice thing to do so that I don't have to do both moments. But again, we can do it either way. So that means we have 800 in the negative plus 600 minus 600. Therefore, it's 800 and the negative or minus 800 Newton. I can remove the A here because we are solving for part A, which asks for only the resultant at point A. Okay, now the resultant moment at A, it's equal to, so again, you can reduce those two, the 800 and 600 into one force and find the moment created by that 200 and the moment created by this 600. That's one option. You can find the moment created by the 800, then the 600, then the 600. That's option 2. Or if you want, we can find the moment created by the 800, and then we have a couple. Okay, that couple, the value for the couple is simply 600 times 2, and it's going in the clockwise, which means it has to be negative. Okay, so it's going to act in this direction. Now the 800 is also in the clockwise about point A. It does make a difference whether you're looking at point A, it's clockwise, or at point B, which would be counterclockwise. The couple itself, it's always going to be in the same direction. As you can see, this is pushing up, this is pushing down, so it's moving this way. So it is clockwise always and at all points. Okay, so let's do now part A and then we'll do part B. So MA, it's minus, that's the couple, 600 times, what's the distance? It's 2 meters. And then minus 800 times 1. So minus 1200 minus 800. So that's minus 2000 Newton meter. So the resultant of these forces, I can replace them with there's nothing in the X, only Ry, which is minus 800 Newtons, and a moment which is 2000 Newton meter. So I can remove 1, 2, 3, and substitute it with these two, the force and the Y and the moment at that point. Again, that's not equilibrium. Now, if I need to do equilibrium, I can actually answer it in 1, 2, 3. The equilibrium would be my support reaction here would be this much and 2000. However, you ignored B, so it's not going to make sense to do it this way, but that's one way to do it. But as I've mentioned, we can't solve this system to make equilibrium, and that's why you have this big note. This is not an equilibrium problem, so we're not solving for the support reaction forces. All right, part B, we need to find the same, but at point B. So now this time here, nothing is going to change for Ry because you can check it. It's always going to be minus 800 plus 600 minus 600. So it's always going to be minus 800. And we will focus on this. We're going to see that that's something called the shear diagram, like these forces. We're going to do that after the next chapter. So first we have the exam, then the next chapter, trusses. And then if you check the schedule, there's something called shear and bending moment diagrams. So we will focus more on these, how they change along beams in general. So again, Rx at B is 0. We don't have any force. Ry is still minus 800 newtons. And then we have M at B. That's equal. We still have the same couple, so it's minus 600 times 2. But this time, as I've mentioned, the 800 is rotating in the clockwise, and the value is 800 times 4, 2 plus 2. That's the distance from the 800 to point B. So it's a plus 800 times 4. So that's 3200 minus this. So it would give me 2000 Newton meter. It seems it's the same, but it's not. This is negative, this is positive. So the difference is 4,000 Newton meter between the two. Okay. The last part, if the two 600 Newton forces were both shifted to the right by a distance of 0.5 meters. So if I take both of them, not just one, just shift both to the right by 0.5 meter, how would this affect your answers in A and B? Explain without this, explain why this is without calculations. What do you think? How would my answers change if I push only the 600s, the two 600 newtons to the right by 0.5, or maybe to the left? If we do each force separately, then you will probably need to calculate it. However, if you notice that those two 600 newtons are forming a couple, and if you recall, the couple is uh, it would always provide you with the same value regardless where you're applying it or where the location is, because it's the same value, because it's always 600 times 2. As long as you move this one by 0.5 meter, this one by 0.5 meter, so it would give me the same result, right? It's 600 times 2 in the negative. So my answer should be for part C. It's not going to affect, what would they ask? How would this affect your answers in A and B? You should say there's no change because the two 600 or the 600 in general, the two 600 newtons form a couple, which would have no change or no difference in value, regardless of the location, as long as we keep the separation distance the same. Okay. So these two problems, this one, the previous one, should review the last section. Sorry, not the last, the couple section. So that's chapter 3. Question number 1 should be a review for the last or the first part of the last chapter, the equilibrium. That's how you find reaction forces. And then the one before that, how you find these two, like that's the last part of chapter 4. So what we have left is also we did the equilibrium in the period in this question 2 here. So now what you have left is probably chapter 1 and 2. Those are very basic. We've seen them, like how to decompose this force into X and Y, how to decompose this force in X and Y. So before we move to the next question, do you have any other question that you want me to solve? We have another equilibrium question coming in problem 5. And we're going to do more of the equivalent in the last one. Should not tip over if the maximum is this. What should be the support specification at the base? Yeah, again, that's equilibrium problem, the last one. Do you want me to go over anything in the homework before we hit, or maybe after I finish this and the next one? Just to manage my time for all right. None. I'll just move. If you have, just let me know. I'll check also my messages if you want to send message if you can't talk. Find their reaction forces at the supports B and C. So this one I need to give you one as pin, the other as roller. Otherwise, we can't solve these systems because we only have three equations. So we need to find the reactions forces, one at C and two at point B. What we have this member AC, and it's held by a pin support at C. So that's RC in the X, because that's a pin, and RC in the Y direction. It has to be vertical, not inclined. And then support B, it's a roller type, so that's RB. You can put Y or just RB. And then we have this cable, which is inclined 512, so that's 512, 13. Okay, it's holding that to this point. However, I'm going to consider this whole bar here. So I'm not going to be looking into this point, but I do need to consider those two. First, this is 780 newtons, and it's the same cable. It's the same color, so let's pick maybe red. It's the same to here. So it has to be 780 down and 780 going this way. That's number one. That's a property of pulley and cables. What's the other one? I can, because I need to get rid of the pulley. So, well, I can actually translate these two into the center without any changes, right? You remember that property? I can move the forces acting outside on the periphery into the center the same way, parallel forces. So this would be 780 down, maybe 780. And this would be, if I draw slightly bigger, that 780 with a slope of 512, 13. It's small, but you can see here, 512 and 13 right here. If you don't, then you will have to decompose those two up to here, but well, what to do? It's pulley and this. I can't solve it. I need to have only one member. And that's why it's tricky. They put that one outside and they gave you the distance just to complicate things. So now if I draw the free body diagram, I'll get here RCX and RCY. I'll get RBY. Here it's 2 meters from here to here. And then I have this force. I have the 780 down. That's the first one. Let's put it in another color so we know which one is which. 5, 12, 13. So I'm going to decompose this one time in the X and one time in the Y. So I got here 780 times 12 over 13. 780. And then 5, the Y, 5 over 13. Okay, so now this becomes a regular equilibrium problem. We should know how to solve this. I have how many unknowns? 1, 2, 3. So we'll start as we always do. We'll take the moment. Let's write here. That's A, that's B, and C. We have 2 meters here, and we have what do we have? We have 3 meters. I was about to put 3.2. 3 meters, meter. Okay, we said the first hint, start with the moment equation. Okay, that's number 1. 2, take it about the point that has the highest number of unknowns. Again, it's not going to make a big difference if you take it about point B or point C because RCX is going to pass through those points. We can actually, the only way to find RCX is to consider the force in the summation of forces in the X or the balance in the X direction. So it's up to you which point you want to take. And I'll take it this time. Usually I take it on the left side. So this time I'm going to take it to the right, about the right. So about point C equals to 0. That means RCY is going to disappear from my equation. You can actually, if you want to reduce the number of forces here, I can say I'm going to have 780 times 8 over 13 going down, or just keep both if it's going to make some confusion for you, and then take only one moment. Because if you start, actually, we're going to start from the left. That's usually what we do. If you start here, it's going to be 780, that's the full, this one, times 5. And then I have here 780. It's going to go in the clockwise. So it's minus 780. 5 over 13, that's the force, times the distance, it's 5. So if you factor out the 5 from here, so you're going to get 780, 1 minus 5 over 13, or 8 over 13. So you could have done it here and reduced this. Oops. What did we erase? Probably this one. Okay, so this one is down, this one is down, this one is going to pass through this point. So next I have RBY minus RB y times 2 meters, and that's it, equals to 0. That's the nice thing about the moments. If you take it about the point that has one of the unknowns, that would disappear, and then I can solve for the other one. Okay, so this would be 780 times 5 times 8 over 13, and then I'm going to take RBY to the other side, so 2 RBY. Therefore, RBY is whatever the answer divided by 2. I get an exact 1200. Let me just do it one more time. $780 times 5 times 8 over 13 over 2. Yep, 1200. And it's what? Newtons? Okay, newtons. Okay, so RBY, it's going to be equal to 1200. And then what we have left, the other two equilibrium equation, X and Y. The X would be minus 780, 12 over 13. And then how's RCX? RCX also in the negative, minus RCX equals 0. Therefore, RCX is minus this answer, which would be Actually, I mixed up. Okay, this one is in the positive. This one, 780, 12 over 13, it has to be positive because it's going to the right. So it has to be positive since I take RCX there. And that would be 720 Newton. And if you do the Y, I have 780 into 5 over 13 going up, minus 780, that's the red one. So that's up. This one is down. That's another place where you can save time if you do it. If you find the resultant of those two, that's 13 here. 13 minus 780 plus RBY plus RCY equals to 0. Okay, we found RBY 1200, therefore RCY is 780 minus 780, 5 over 13, and then minus 1200. And this should be negative. Actually, I got minus 720 newtons. Okay, all right, let's head to the last problem. I thought would be done earlier. So I'll go a little faster because we did solve this, something similar to it. It's don't get scared. Do you want me to wait here? Maybe 1 minute, 2 minutes? If you're done, let me know. Just anyone, if you can open your mic and